Sorry about that. Mike was muted. Welcome to CENG 15. What we're going to do is pick up where we left off on Monday's class, last lecture, something like that, with our random walk. We had finished the simulation portion of it, right? We had gone through the 100 steps that we were going to do. We had started the plot. We got it more or less the way that we wanted. We noticed some weird things. We couldn't tell where the particle was when it was done. The steps were supposed to be square, but they kind of looked like a rectangle. So we're going to finish those up. Those are more just to kind of see it the way that it ought to look. It's not going to add anything to the analysis. We are, however, going to go a little bit further and introduce sort of an engineering concept of log-log plots and what we can learn from those. Because in your, I think, second to last homework problem, or maybe your last homework problem, you're going to be asked to use this sort of an analysis of random walks in the context of a log-log plot to learn something about randomness. Even though we are making a completely random step, left, right, up, or down, the distance that we displace off of our starting point still scales in a predictable way. And that predictable way is what you're going to investigate on your homework. So let's switch back over and wrap this up. I don't think that we're going to be able to get to MATLAB today, so we'll probably start fresh on Friday and really dig into MATLAB. And that's where we will likely find ourselves at the end of the lecture today. We might finish a couple of minutes early, but I'd rather finish early than try to start up MATLAB and then run long. So that's what we're looking at. Let's go ahead and switch over to Excel. So this is the worksheet that we were on yesterday. Just as a review of what we were looking at, we wrote some pseudocode over here for the type of simulation that we were going to perform. We summarized all the different possible steps that we can take inside of our simulation. We're actually going to come back to this later today, towards the end of today, to look at other ways to make that kind of a choice. We had written a couple of comments to ourselves on the pseudocode about, we start with an initialization, and then we perform a simulation loop, and then we do some kind of post-analysis afterwards. We were a little bit premature marking the plot as complete, so I'm going to unmark that as complete because we're going to finish that up. The set of vectors, or remember really, if you were to think of this all as one big data set, this is a big matrix, but we kind of thought of them as columns, right? We had a couple of columns over here for the sort of starting values of x and y. We picked a random number, and then based on that number, we determined the direction of a change and what that looked like for a displacement, and then calculated the new values. One of the key steps in there was that each time we go to the next step in our simulation, we link backwards and say, okay, whatever the new value was, that now becomes the old value for this set of the simulation step. And that got repeated all the way down as we went. When we were all done, we plotted these old values, and remember, we plotted the old values rather than the new values because we wanted to start at 0, 0. If you plot the new values, it sort of includes that first displacement already, and that's not what we wanted. And we got a plot that ends up looking like this. I don't know what that 2 was over there. This was our plot, and we said it looks okay, but as we sort of rerun the simulation a few times, so all I'm doing up here is just typing the letter A. Anytime you make a change to this spreadsheet, the random numbers will regenerate themselves. You can see everything kind of changes a lot, and sometimes the steps don't look like they're squares. So here's an example where it looks like you took a step further in the vertical direction than you do in the horizontal direction, and that's not accurate. The reason for that is nothing wrong with our simulation. We just have to pretty up the plot a little bit, and we want an equal aspect ratio on the x and y. Just from playing around with this a little bit, it looks like we never really displace more than about maybe -20 to +20 in either direction. So we can square up those axes if we just force them to always be between -20 and +20 on the x and -20 and +20 on the y. I'm going to go through that fast. If you don't know how to set those, you can rewind the video afterwards when it gets posted on YouTube. But it's not critical to the analysis, so I'm just going to describe what I'm doing, but go through it fairly quickly because we've already done it a few times. So we're going to format the y-axis by right-clicking on it, and over here under axis options, we're going to set the bounds to be -20 and +20, and I'm going to set the units to be 5 just because it looks like a decent step size in between there. And then I'm going to click on the x-axis and do the same thing and set that to be -20 up to +20 with major units of 5. So what that guarantees is on a plot window like this, there will always be the same number of units on my plot going left and right as there are going up and down. As long as I then make the plot look on the window roughly square, I should end up with steps that look roughly square. You can still mess it up if you were to drag your plot and make it very sort of strange and elongated that way, but as long as you grab the handles of the plot and make it look roughly square, you can just eyeball it. It's not critical to the analysis. Then everything should look pretty square. So as we change values on here, we can watch our plot update as it goes. And we're only going 100 steps here. In your homework, you're going to do, I think, 5,000. So your bounds on your axes will probably have to be a little bit bigger. You can set them to whatever you think is reasonable. If a handful of your simulations happen to go off the plot, it's not a big deal. That's okay. We also want to mark the starting point, the stopping point. So wherever the last value is where our particle is. So we're going to add that. We're also going to add, for visualization purposes, a line that connects where we started to where we finished, because that length of that line is the number that you're going to be calculating in your homework. I don't ask you in your homework to plot the line, but it's nice if you've got a visualization for it. So I'm going to create a little table over here just to summarize the extra points that are being plotted. Again, not strictly necessary for a homework. I like it because it organizes my thinking a little bit, so that I can figure out if something's going wrong, where do I look for something going wrong. So let's put final location over here, and remember any plot point on a 2D axis is going to consist of an x location and a y location. The x location is just going to be the last x location in our vector over here. So I'm going to come down to the bottom one and click on that. Notice it's not the maximum, right? It's the last one in the vector, but it's not the maximum value of x. It is possible for you to go off in one direction and then come back in the other direction. So it's not max. You don't want to use a max function there. It's just the last function. And then the line that's going to connect these, I'm going to call this the displacement line. And we're going to talk about how to calculate the length of that line. It's not a complicated formula, but you might need to be reminded a little bit. Remember, the line, if it goes from the origin to the point, that means its initial xy is always going to be 0, 0. And its final xy is just going to be the same x and y that we had just calculated a moment ago, which is wherever the particle ends up. So it's not that much different to add a line than it is to add a point. It's a little easier to add a line on here because the scatter plot that we're using connects points by straight lines, so we'll have to play that little finicky game with the point location to actually visualize it. So to add these to my plot, let's move it up here so you can see it. I'm going to right-click on the plot and say Select Data. I'll just rename the trajectory as trajectory, just so that I know what it is when I'm looking at that list that's on there. And then I'll add a data series called Final Point and just select the final x and the final y that I summarized over here. And I'll click OK. And if I look over at the plot, nothing has changed, right? The point is on there. It's just that the plot style that we're using connects points by straight lines without any markers. So we have to play that game that we did, I think it was last Friday, when you have a point on a plot that looks like straight lines, you have to sort of go through a different method of accessing that point. So I'm going to unhide my ribbon up here so that we can see it. I've got my chart selected, and then I'm going to go up here to Format, and then in the top left, I'll select the final point out of my drop-down menu over here, because that's the series I want to edit. And then I'll say Format Selection, and instead of a line, I'll say No Line, and the marker, I'm going to set it to be a circle because I like circular markers, but you can set it to be anything you want. It doesn't have to be a circle if you want. And I'll set it to red so that we can see it nice and clearly against the black line that's on there. So there's our red line. I'm going to reduce the weight of the black line a little bit just so that we can see it a little bit. That red marker kind of pops when the black line is a little bit thinner. And then we add one more data series, which is to add the displacement line. So we're going to say select data, add another one. This one we'll call the displacement line. And we'll just select the two x's here and the two y's. And we've got our line, which is a little easier to interact with than the other ones. So I can say format data series. There's no markers on this one. We can adjust the line. I'm going to make it a red dashed line just so that it stands out a little bit different from all of the other ones. Red, not, there we go. So now I've got this little dashed line that connects my point to the origin out to wherever the final location is. Let me see if I can run a couple of these real quick so we can see a good displacement. That's a pretty good displacement line. Let's leave it there. That distance is the one that we're interested in for our kind of post-analysis in an engineering sense. Now that we've kind of completed the code, what can we learn from it? That distance behaves a particular way as you increase the number of steps, and so we want to be able to measure that distance. It can, if you have too many points on there, by the way, it can be a little crowded on your plot. You may also wish to actually delete the axes on this one, just to make it a little bit easier to see. But I recommend you set the scales on your axes before you delete them, because otherwise you have to add them back in there and then change them. Just a little side note about as this plot scales up a little bit to more and more points, you might want to just delete the axes, which is okay for us. Oops, I screwed it up. Oh well. We had a really good plot on there. There's another good plot. We want to measure that distance L. In order to do that, we have to measure the displacement of a particle on a 2D plane. Anytime we want to measure a distance the particle has traveled on a 2D plane. Anytime we want to make that kind of a measurement, and it's going to come up a lot in the, not just the homework, but the other simulations that we're going to do. The distance between 2 points on a 2D plane is given by an equation that probably looks pretty familiar to you. It's just the old Pythagoras equation. If you have a point here and a point here, all we do is say if I want to measure this particular distance d, we assume that it forms a right triangle, which it does. And if this is your displacement in the x direction and this is your displacement in the y direction, then the distance you travel is just the square root of the sum of the squares. So we take the distance traveled in x and add it to the distance traveled in y, square both of those, and then take the square root of that. Just a little callback to geometry there. It shouldn't be new, but just as a reminder, because maybe you haven't used it in a while. So we're going to call that displacement here r. So that dashed line, red line that we've got over there is r. And we get a little bit of luck compared to the general case. The luck that we get is that this point is always at 0, 0. Right? We always start at 0, 0, and we always go up to x, y. So the displacement that we're interested in calculating is actually a little bit easier since there are a couple of zeros in there. It just becomes equal to the square root of x squared plus y squared. If you don't start at 0, 0, right, if you don't start down here, then you have to use the difference between the 2 points in the general formula. Oops, I'm a little bit behind here. There you go. There's our formula. As I said a moment ago, but failed to highlight it, because we've got 0, 0 down here on our origin, and it will always be relative to 0, 0, our code simplifies, or our function simplifies a little bit, and just simplifies to the final x and the final y squared, and then summed, and then taking the square root. If you don't start at 0, 0, if, for example, maybe you want to find the displacement relative to the last step that you took, then you have to worry about the delta that's up here, right? You have to say final minus initial and final minus initial rather than the present spot minus 0, 0, the origin. So we get a little bit of that simplification here on our random walk. but that's just for a random walk. There will be other times where you just need the displacement between an arbitrary set of points, and then you can use that formula that's on here. So we're going to calculate the displacement at every step of our simulation. Since we've already got column vectors over here, let's just add another column vector as r, right? This will be our displacement. All we have to do is take exactly that form. I'll scooch over a little bit here so that you can see it. Let's actually shrink a couple of these a little bit just so they're a little bit more narrow and we can see everything that's in there. There we go. So if I want to calculate the displacement, I say take the square root of whatever the x value is squared and add to it whatever the y value is squared. Notice I'm using the old values again, not the new values, because that's the set that we're actually plotting on here. The new values just get updated into the old values on the next iteration of our simulation. And then I can double click to autofill that all the way down through the bottom, which if you think back to a last lecture, that's a style of iteration, right? We're going through and calculating the same thing over and over and over again, just for slightly different conditions. Your homework is going to ask you to analyze certain features of this displacement, but only at particular points. And I will show you the points first, and then we'll talk about why I chose those particular points. So the summary displacement table, which is something that you're going to have to create in your homework, only asks you to look at how far you've gone after a certain number of steps. So the steps taken that you'll have in your homework follow patterns that look like 1, 2, 5, and then 10, 20, and 50, and then 100, 200, and 500. I'm going to talk about what that pattern represents here in a moment. It might seem kind of arbitrary right now, but we will get there in a moment. And then the displacement table is only interested in those values. We've got to calculate them all, right? Because the current one depends on the previous one. But we're only interested in looking at a few of them, which is this 1, 2, 5, and then 10, 20, supposedly 50 later. And we want to extract the value of r from that. So I'm going to let you try to extract that value of r. What you're trying to do, and I will scooch over to the side a little bit, is index into r and get the corresponding value. So this cell should get the first value of r, this should get the second, this should get the fifth, this should get the 10th, etc., etc. I'm going to give you a little bit of time to try that. Let's come back at about 321 and see how far into that indexing procedure you can make it as a little bit of practice here. And I'll double click on the expression that we used for r over here, just so that you can see it. All right, we're back. It's about 3:21 now. So let's use an index function to get into those cells and figure out what the corresponding value of r is. So we start off with index, and then we provide the vector that we're interested in indexing into, which in this case is r. We're going to lock that cell reference, so we add the dollar signs on there, because as I drag this formula down, I always want to be indexing into the same vector r. The value that we would like to extract, the row, corresponds to this step number that's next to us here. So if we want the distance, after one step or two steps or 5 steps, the general pattern is go the number of steps equal to this number that I've typed next to me over here in R. So we'll close that and then drag this formula down through here. So it kind of looks like it's going up a little bit. It's a little hard to see with only 20 steps on here, which is why in your homework you're going to go up to 5,000 steps. The pattern will become a little bit more obvious there. One thing that you'll need for the pattern is to take these values and now run the simulation 10 times. In order to save that data, you have to save it in a particular way, because if I change anything on the sheet right now, if I hit A, for example, all of those numbers will change, right? As I change something on the sheet, those numbers change. I would like to be able to store those values somewhere and hold on to them for future analysis. The way to do that, because we're dealing with random numbers, that will update every time, is a particular paste operation. So to save just the numbers, use paste values. So for example, let's say we want to do a simulation, a first simulation, we'll call it R1, right? What's the displacement from R1? We take these values here, which are the displacements for the particular simulation we're running right now, and I hit Control-C on my keyboard, or Command-C if you're on Mac. And then in order to paste them, if I were to just come down here and hit Control-V, or Command-V, you'll notice we get a bunch of junk. I don't even know what a spill error is. I've never seen a spill error before this morning in Excel. It probably has something to do with indexing. But at any rate, just a plain old copy-paste doesn't work because it takes the formulas and not the values. So instead of that, if you highlight the values you want to keep, Control-C to copy them, then right-click where you want them to go and go up to the top under Paste Options, and you'll see a value that looks like, or an icon that looks like a clipboard with 1, 2, 3. That means go to the clipboard and paste the values that are on that clipboard and not their formulas. And if you click that, now the numbers that are here are locked in place, right? They will always be that set of numbers. That's all that you've copied. So to do more and more simulations, you just add more and more columns here, and you come up and copy these, right-click, paste values, grab another set. Actually, those didn't update. Oh, those did update. We just happened to displace the amount that was equal to the previous one. And now you're generating a table of multiple simulations, right? We've taken multiple random walks here and looked at the displacement after that number of steps, however many number of steps we had, which in this case was 1, 2, 5, 10, and 20. So this is the table that you'll eventually have to create a plot to learn something about randomness. We're going to talk a little bit more about randomness here in a moment. But I do just want to pause because I talked about an awful lot of stuff there and give you a couple of moments to ask any questions if you have them. We're pretty much done calculating anything with the random walk. We're only going to talk about concepts for the rest of the lecture. No more like actual calculations. So I'll just pause for a couple minutes. If you've got any questions, feel free to throw them over into the Canvas chat, but we'll give you a chance to catch up here as well. All right, so what is the pattern that we're looking at? I'm not going to look, that's actually described in the homework. I'm going to focus a little bit more about how do we identify the pattern that we are looking for in this set of randomness. In order to do that, I want you to know a little bit about how log-log plots work or log scale plots work, because that's what you're going to have to create on your homework problems. Just as a quick note of how to get log-log plots, the way to get a log-log plot is to go into your axes. So you can go to either the horizontal or the vertical axes, format it, and then right underneath, oh, where did it go? Oh, the numbers are actually gone, aren't they? Let's add the axes back into here. I deleted my axes, so let's put them back. We'll go in here and format the same place that you went to hit the bounds for -20 and +20, or set the bounds. Underneath that, you'll see this button that says log scale. And so you can click that. It's not going to work here because we've kind of messed up the bounds a little bit to be negative numbers. But that's what you'll eventually have to click on your plots in your homework, is to set this scale to log scale. And we always leave the base as base 10, although technically you can change it. So that's how you set a plot to be log scale. And you have to do it twice, once for the x and once for the y. But what is that accomplishing? How do we interpret a log scale? What is a log scale, for that matter? Let's do a little bit of discussion about what a log scale is. First of all, what it is another way of scaling the x-axis. So this, or I shouldn't say hex, any axis, it doesn't matter if it's x or y. A linear scale would look something like this. I start from a particular point, and then at every distance out through here, the distance between those 2 points is a fixed amount. So the most common one that you have probably seen is something like 0, 1, 2, 3, 4, all the way out to whatever you want. It doesn't have to be 0, 1, 2, 3, 4. It could be, say, 10, 30, 50, what would that be, 70, 90, right? Any time where the distance between adjacent points on your axis is the same, that is going to be a linear scale, right? The distance between those 2 points is the same. On a log scale, that's not the case. So if you start from a particular point and go out to here and draw your tick marks, the distance between tick marks on here represents an order of magnitude. So if you start from 1, you'll go up to 10, and then you'll go up to 100, and then 1,000, and then 10,000, etc., etc. So now, instead of the same distance here, what we have here is a factor of 10. It can be a factor of other stuff too. It could be the other one that sometimes gets used as a factor of 2. I can't say I've really ever seen too much more than a factor of 10, and then very rarely a factor of 2. Factors of 2 come in like signal analysis and stuff like that. But most commonly you'll see it as a factor of 10. This is a log scale. Now, the advantage of a log scale comes when you use 2 of them, when you use what we call a log-log scale. Something to keep in mind when you're going through a log scale is, let's say that you zoom in on a particular element of it, right? Let's say you want to zoom in on this down here, and the lower value is 1 and the upper value is 10. The halfway point on a log scale in between 2 tick marks is not halfway in between the 2 ticks. What you'll see is that the halfway point is closer to 2. It's not exactly 2, but it's close to 2. And then they start to bunch up on the other side. So the 3 might be somewhere around here. The 4 might be a little bit closer. The 5, the 6, the 7, the 8, and the 9, they all kind of bunch up a little bit higher. So the higher values are up here, are something like, the 7s, the 8s, and the 9s, and even the 10. They all kind of look like they're sitting right on top of each other. So a log scale is designed to show you what's happening over very large orders of magnitude. It's not designed to show you very small orders. So doubling something or even tripling something doesn't have a big impact on a log scale, because all of those numbers end up getting bunched really close to the 10. The other thing to note on a log scale, before I get to that log scale that I now alluded to several times, is that they can never go negative. So they're never negative. So if you have an axis that looks something like this, and it's a log scale, it could be something that looks like 1, 10, or 100. More generally, we would represent that as 10 to the 0 power, and then 10 to the first power, and then 10 to the second power. It's those numbers in the exponent, those are allowed to go negative. But the resulting quantity that we actually plot is, of course, never going to be negative, because 10 raised to a negative power is not a negative number, it's just a tiny number. So as another example, we could do something like, say, 10 to the minus 1, and then 10 to the 0, and then 10 to the 1. That would correspond to plotting 0.1, and then 1. Oops. Thing moved here. And then 1, and then 10 up here. Right? Those are all okay, but no matter how small that exponent gets, 10 to the minus 9 or something like that, it just means there's a lot of zeros, and then there's a 1. But you can't actually go negative on a log plot or a log scale. So that was the source of the error that you saw a few moments ago when I tried to take our plot of our particle and see what it looks like on a log scale. You can't do it because some of those numbers are negative. That's just not defined on a log scale. The key feature, and the one that I want you to keep in mind, the one that will actually be of use on your homework, is that on a log-log scale, so that when I say log-log, that means the x is on a log scale and the y is on a log scale. The slope is equal to the power. And what I mean by that is that if on a log-log scale you have a relationship like y is related to x, then the slope is equal to the power of the x that's up here. So x raised to the p. I don't mean like power as in some sort of statistical power. I just mean it's that value raised to a particular power, which is one of the nice uses of a log-log plot. If you ever want to convince somebody that a relationship goes as x squared or x cubed or x to the 1/2 or x to the 0, or I should say x to the 1, like a line or something like that, one way that we display that kind of behavior is on a log-log scale, or on a log-log plot, if that's what you're going to generate. So, for example, the plot that you're going to generate, what you want to do is set the number of steps taken over here versus the displacement r over here. As long as these are on a log-log scale, so let's say that I'm going to try to get these close and say maybe 1, and then this is 10, and 100, and 1,000. As long as they're going up, as long as this distance here on your plot looks the same as that distance there on your plot, then you can read off the slope and verify that it behaves a particular way. So it doesn't actually matter what this value is. Let's say that, I don't know, we start at 0.1 and then go up to 1. Right? It's not that they have to share the same numerical values, it's just they both have to be on a log scale. The data that you'll end up seeing, let's sketch in the grid lines here, should follow a straight line if you view it on a log-log plot, which is the way that we're viewing it right now. I'm going to remove my grid lines on here. So, for example, if you collect all of those r values, what you may see is that that looks like this, right? It might look like a slope of this style. And if that were the case, then this is saying y scales as x to that slope. Or it may look like a straight line that looks like this, right? And what this is saying is that y is scaling as x, but raised to a different slope. And that's a hallmark of something that obeys this sort of exponential or power style relationship, is that if you raise it to that particular value and then plot the result on a log-log scale, you should see a straight line. And that's a nice engineering style relationship that you should keep in mind, because often when we are interested in a value that changes over many orders of magnitude, we're less interested in the exact number, the exact quantity of that parameter, and we're more interested in how does it change over many, many orders of magnitude. Log scales can help us figure that out, and if it happens to be a straight line, like the ones that we've got here, then that straight line is proportional to the power, the exponent of your independent variable, which in this case happens to be n. And so the relationship that you're going to discover in your homework is that r will scale as n to a particular power, right? You'll find the power that sits on there and determine it experimentally, or in this case with a simulation, which is essentially an experiment. So that's log scales. That's something that you're going to have to generate in your homework. The other thing that I want to get back to is a different way of doing the simulation. So let's ignore the log scale for now, kind of encapsulate that and leave it aside. The other element that I want to talk to you about is a programming tip or a programming approach that we can use in lieu of the way that we've done it here. So let's look back at our simulation over here. And recall that the way that we set up this random number generation was to pick a number between 1 and 4, and then we would look in a table to determine whether we went right, up, left, or down. That table was over here, right? This summarized all of the possible directions that we could go, as well as what those looked like on a 2D axis, right? Whether we displaced to the right or left or up or down, we enumerated all of those possible outcomes. There are other ways to do that, and I want to talk about a few of those other ways. So in order to do that, I'm going to take this this table, and move it over here to a new sheet. Oops, I lost it. We'll zoom in a little bit so that you can see it. And what we're going to look at are cases and if statements as alternatives to essentially generating this table that we want. So as an example, we could use the choose function to select from cases. The way that this works, at least conceptually, which is what I'm going to draw up here. Let me move my cursor a little bit just so that we've got it over here. The way that we would write this in code is we would want to work as a switch based on a case. Switch is a keyword in most languages, so I'm actually going to erase that and turn it blue because we want this to be blue. Which cases are we interested in here? Well, we were generating a random number between 1, 2, 3, and 4. The various cases that we can have are case 1, we're going to the right. Case 2, we're going up. Case 3, we're going left. And case 4, we're going to go down. And it could be in any order, right? We just pick those arbitrarily. It could be left, right, up, down if you wanted to do something like that. But at any rate, we are going to input a number, right? We're going to pick a number between 1, 2, 3, and 4. That is our case, right? Our case can be either equal to 1, or our case can be equal to 2, or our case can be equal to 3, etc., etc. And then once we know 1, 2, 3, or 4, that's saying return the appropriate value. So if our case was 3, we want to return left. We already saw one way to do that with indexing, but there are other ways to do it with something like what we've got here, which is a switch statement, or using a choose function in Excel is what that's called. So the syntax to use that in Excel, to create a switch statement, use the choose function. So for example, what we would end up doing for a case like this, where we could go right, up, left, or down as cases 1, 2, 3, and 4, we would say equals choose. We would give it what we would call the case number in this case. which is very similar to the index that we had used when we were indexing into something. But we would give it the case number, and then we would enumerate the different cases that we have. So the first case, if the case number is 1, is that we went right. If the case is 2, that means we went up. If the case is 3, then we went left. And if the case is 4, then we went down. So I'm going to repeat that over here. We'll say case number and result. Let's say the case number is 3, right? Normally we would do this with a random number generator, but I don't want it to change over and over and over again. So I would say choose, and what do I want to choose? I want to go into a case number, which is the number that's next to me, and then I want to return right, or up, or left, or down. And you can put as many of those in there as you want. If you look at the pop-up window that showed up as Excel was auto-filling this, you can add value 5, value 6, value 7, etc., etc., etc. So what are the similarities and differences between the indexing? The similarity is you can visualize a vector of values there, right? There's still the right, up, left, and down. But the difference is we didn't actually turn those into a vector. That vector exists in cell B2 through B5 up in the top left corner. But here we're actually enumerating that vector inside of our cell. And it's not really a vector, it's actually picking cases. It just looks very similar to a vector for something like this. The other difference is that when I finish this function and then enter out of it, I can no longer see what my cases were. If I want to see those cases, I have to at least hover on the cell, or more likely, double-click on it. I can't see them summarized as a table anywhere on my spreadsheet. They're just contained within that particular cell. It's not really a good or a bad thing. It just depends on what you're trying to accomplish. Personally, I like to see them enumerated somewhere because it reminds me of what the different cases are. And so I can check very quickly that 3 should be left because I've got them enumerated over here. But if all I have is that choose, it might be faster to write it. It just becomes a little bit harder to debug it, right? To say, wait, was 3 actually left, or was 3 right, or was 3 up? I have to come in here and kind of count and say, oh yeah, left showed up as the third element. That's the third value. It's just an extra hoop to jump through. But if it's a simple case, it might not be that difficult, right? There's only 4 options here, so it might not be that hard to track it down. Similarly, if we're doing the dx displacement, and I'm not going to go through the dy as well because it'll look similar, what we would do here is say equals choose. Which one do we want? We want case 3. Well, now we have to enumerate the numbers that could potentially come out. So if we were to go to the right, it would be 1. If we go up, it's 0. If it's left, it's -1. And if it's down, it's 0. Right, this is a case where I was able to write that pretty quickly because I can look at it in that little summary table in the top left. It may or may not be easy for you to enumerate what the choices are for dx and then similarly the choices for dy. But if you can, you're more than welcome to use the choose function on your homework or in any additional problem afterwards. Choose is just fine. It is doing something subtly different. It is making what we call a switch statement where you're picking from different cases. As opposed to indexing into a vector, those are 2 distinct operations. I'm bringing them up here because we've already got something to work with, which is the indexing, and I would like you to be able to compare the differences and see how they compare for both similarities and discrepancies. So choose case is one option. You can also use an if statement. So use an if statement to select based on a criteria. Even criteria is not really the right word. I would say comparison is the right word. So switch statement or a choose function like we did before, that has clearly enumerated cases. It can only be case 1, case 2, case 3, or case 4. But you can also make decisions based on comparisons, such as if a particular value is less than another value or greater than another value or equal to another value. If you want to have that level of flexibility, then you're going to need an if statement. We're not going to take the if statement very far here other than to look at its general syntax because it doesn't work particularly well for the type of decision that we have to make here. We're going to use it again when we get to our next simulation of ideal gases because it works a little bit better there when we have to make sort of simpler comparisons. Here, the if statement can work. The problem is that we have to do what's called nesting an if statement. So the general syntax for an if statement, at least in Excel, and you have different syntaxes elsewhere, is that you ask Excel to calculate if the condition, right? You provide the condition first. You give it then what happens in the true case and what happens in the false case, which almost all if statements are going to work that way. It's just a question of how do you actually provide it to the computer. Here it kind of goes horizontal. In MATLAB we'll see it kind of goes vertical. But they're all doing this, right? You give it a condition. What's the condition? Well, the condition could be something like, if x is less than 1, or if y is greater than or equal to z, or something like that, right? It can be a comparison in that sense. Here, our conditions that we're interested in are things like if the random number is equal to 1, right? Or the random number is equal to 2. So we're kind of listing out the same sort of cases that we saw before. The tricky part is the true cases and the false cases require you to use additional if statements because you kind of cascade through a series of decisions, which we're going to do an example of here now. It's a little bit more complicated than it needs to be. A choose statement is a little bit easier, but I want you to see how it works. If you thought an if statement could do this, you're right. It just looks a little bit worse. So let's bring our case number and our result down here. And let's sort of look into what this would look like. Instead of a case number, right, in an if statement, we're basing it on a comparison. That comparison takes place inside of the if statement. So I'm going to type equals if. As the pop-up shows you here, we have to provide a logical test. That is our comparison. That's our condition. And so what do we want to start with? Well, the first one is that if this value is equal to 1, right? And we're going to go through 1, 2, 3, and 4 and kind of show you why an if statement kind of looks a little bit ugly for this case, but it can be done. If it is equal to 1, then the result that we had before is that we would like to go right. So we give it the text that it says right. If that value is equal to 1, go right. What happens if it's not equal to 1? Well, now we have to test all of the other cases inside of the false case. So we have to put if statements inside of if statements. That's the annoying part. It's not impossible, but it's a little annoying. So if it's not 1, maybe the next thing that we want to check is F29 equal to 2? If it's equal to 2, that means we must have gone up. If it's not equal to 2, that means it's not equal to 1 as well, but we need to check whether or not it's equal to 3. So we say, is F29 equal to 3? If it's equal to 3, great, that means we are going left. If it's not equal to 3, we've now finished all of the possibilities for this example, right? It can either only be 1, 2, 3, or if it's not 3, then it must have been 4, and the only resulting value is down. So we put quote down on here. And so that's one of the levels of trickiness for if statements on this particular example, and why I don't really recommend it for this example is because you need to sort of nest the cases this way. Or you can spread them out and then do some clever math afterwards. If this is appealing to you, if that's the way that you saw this getting set up in the first place, you are more than welcome to use that on your homework. If it's not appealing to you, I wouldn't worry about it. We're going to come back to if statements on our next project when we do ideal gas simulations, where we don't have to nest them in quite this way. It's a little bit easier to see this nesting on MATLAB than it is in Excel. But I will go ahead and close this off just so that we can see what that statement would look like. If we hit enter, it will behave the same way, right? If I give it case 1, it still goes right, 2 is up, 3 is left, and 4 is down. It's just it took a little bit more work, right? I think that looks kind of ugly in order to interpret that in a human readable way, but the machine interprets it just fine. You can use whatever is more comfortable for you on the homework. They will both, if done correctly, give you the same answer. So that is the last of what we want to do in Excel. We are going to wrap it up here for today. When we come back on Friday, we're going to start into MATLAB and then stick around in there for a little while before eventually moving on to our next simulation, which is of ideal gases. So I will wrap it up here. I will stick around over in Canvas chat. If you have any questions on anything, please feel free to throw them up over there. Otherwise, stay safe, stay healthy. I may see you tomorrow in office hours or maybe on Friday in lecture. Either way, have a good one all, and I'll talk to you soon.